Now, let's talk about this portfolio theory, which in sometimes in a more elaborated way also called as mean variance portfolio theory, or in some other words, it's also called as modern portfolio theory, MPT. Primarily, what this talks about is how can I construct a portfolio, the basic foundation for constructing a portfolio in such a way that if I have chosen some amount of risk, I will get the maximum possible return for that specific risk. Or if I have chosen some specific return, how do I build or how do I expect to get that particular return where I take the minimum possible risk? So this is what is the typical background behind the portfolio theory. We'll discuss about this theory in detail, but yes, there are just like any other theory, even this theory is also based on a set of assumptions. So this theory is more and more effective, more and more applicable only when these assumptions are satisfied. And one more thing is it is more and more focusing on the assets per se, asset and the returns on the assets, but in its prime form it is ignoring the liabilities in terms of the computation of the optimal portfolio. So that's one major limitation that we need to be understanding. It is considering the assets, the return of the assets, building a portfolio based on the concept of mean and variance, but it has ignored the liabilities in its basic model. Probably it's not that difficult. We can very well extend the model to include the liabilities as well. So just getting a little bit more detail in terms of understanding this. Here I talk about a two-step model. If I have to understand this, I talk about a two-step process. First, let me identify the opportunity set. What is this opportunity set? Those particular portfolios which are available to the investor. Which all portfolios are available? And what are the properties of all of them? When I say properties here, majorly the focus is on the mean and the variance. So define which all portfolios are available. That is what we call as the opportunity framework, opportunity set. And out of all these various portfolios that are available, how do the investor typically choose the one that is the most optimal out of this opportunity set? Which one is the best that is suiting to his requirement? And this is called as optimal portfolio selection. So any portfolio analysis typically consists of these two steps. First, I need to really identify which all securities and portfolios are available, and out of all those portfolios that are available, how do I choose the one that is typically the best? And now the next part is, yes, portfolio theory is very effective, very strong, but as we discussed in the beginning, it has its own set of assumptions. Sometimes they are very unrealistic, may not be more applicable to the real world. These assumptions are primarily from the perspective of what is that the investors typically think. So the investors, how they really think about making their decisions. This model makes a very broad assumption that the investors are typically taking the decisions or selecting the portfolio purely based on the two concepts, mean and variance of the returns. Every investor knows what is the meaning of mean, what is variance, and he is making his choosing selection decisions purely based on mean and variance, which is also making an assumption that there is no irrational investor. All the investors are rational enough who can make their decisions based on the mean and the variance. And it also talks about that all investors have the same time horizon. All of them look at a one single period investing only, which means there cannot be a differentiation between short-term investors and long-term investors. And even in the short term, there can't be a differentiation between someone who wants to invest for a day and someone for a month. So this is one major assumption which may not hold in the real world, and it's easy to compute the mean, variance, standard deviation, correlation and covariance between the securities which constitute the portfolio. All the details are known very well in advance. And apart from that, it also makes something to do with the behavior of the investor. The major assumptions that it makes regarding the behaviors are investors are always non-satiated. What is this non-satiated means? They always prefer more to less. So, for a specific level of risk, the simple way to interpret this is for a level of risk. If I fix the risk, they will always prefer the portfolio which is giving the highest possible return, nothing below it. So this is one assumption that has been made, and along with that there is also another assumption which says they have a big aversion to risk. The investors are risk averse, they don't like risk. So which means now if I have a given level of return, they would always try to choose that kind of a portfolio which is having the lowest possible variance or standard deviation, which is a measure of risk. So these two things mandatory as a part of the decision taking behavior of the investor. And along with that, yes, the market does not have any kind of transaction costs, means probably people don't really make any kind of difference in their decisions based on the transaction costs and the taxes, which is a very unrealistic, but yes, this model had made that. And any amounts, there is no restriction on the amount and the number of shares, number of units that can be held. It can very well be a decimal. Unlimited buying and selling can typically happen. No restrictions with respect to buying and selling. Even the fractions of the units can be held. So all these things went in as the key assumptions as a part of this mean variance portfolio framework, right? So using all these things, it is simply understood that whenever I'm talking about any kind of a portfolio, understanding the properties of the portfolio, it is purely expressed in the form of mean and variance. I need to be in a position to compute the first order movement as well as the second order movement of the portfolio, only that much. So mean is more focusing on the return aspect. Variance is typically more on the risk aspect. We know that the variance or the standard deviation is the typical measure of the risk of the portfolio. Now, just to understand, if at all I require, what do I need to to compute the mean and the variance of the portfolio. We know that if at all I am having, let's take a case of two securities. I am having two securities A and B. A is giving a return of RA, B has a return of RB. And A is having the volatility or the variance VA and B's variance is VB. Now, let's say I have invested WA in A and WB portion. This is the proportion of investment, which means WA plus WB is equal to 1. I have, let's say if it is 60%, WB is 40%. I have invested 60% in A, 40% in B. So WA is the investment here, WB is the investment here. Now, all it says is the expected return of the portfolio is nothing but WARA plus WBRB, which is a clear indication for me here that if at all I have to compute the expected return, I need the individual returns RA and RB. That's one thing which I require. Then if I have to find out the variance of the portfolio, the formula typically comes out WA squared, the variance of A, WB squared, the variance of B, plus 2WAWB, the covariance between A and B. Now this is clearly saying that if I have to compute the variance of the portfolio, I require the variance of the individual securities as well as the covariance, which is a pairwise value between A and B. So in short, if at all I have to find out the mean as well as the variance of the portfolio, if there are n such kind of securities in the portfolio and I want to find out the mean of the portfolio and the variance, all I require is n different means I require, which is the means of each of the securities. I require n different variances, which are the variances of each of the securities, and pairwise covariances between each. So I require NC2 covariances because pairwise. I need NC2 covariances, which is nothing but n into n minus 1 by 2 covariances. So which means all I require is n plus n plus n into n minus 1 by 2, which is n squared minus n by 2. And simplified, it is if I take out half out, this is 4n minus n, 3n plus n squared. And in other way, it is nothing but n into n plus 3 by 2. I require these many observations if I really have to go ahead with my portfolio. I require n into n plus 3 by 2 observations. Both the mean as well as the variance of the portfolio can be computed. Right? Now, once I am able to typically establish, or once I am able to do some kind of a computation, how do I know whether a particular portfolio is efficient or inefficient? Right? I compute the mean of the portfolio, the variance of the portfolio, but once I compute it, I need to know whether that portfolio is efficient or inefficient. As simple as this. Now, let me choose one particular portfolio which is having a mean of Rx, variance of Vx. Now, for this particular Rx, which is the mean return, if I am able to find any other portfolio which is having a variance of less than Vx, then that portfolio is inefficient. If I'm not able to find any other, which means this is the lowest possible variance, then I say this particular portfolio is an efficient portfolio. Or I look at it the other way. If I am going with a particular variance Vx, I'll see from the various opportunity set, is there any other portfolio which is giving me a return which is greater than Rx. If the expected return of it is greater than Rx, then this particular portfolio will become inefficient. But if I'm not able to find any other portfolio whose return is greater than Rx, but the variance is Vx, then I classify that particular portfolio as efficient. In short, for a particular level of risk, if I am not able to find any other portfolio which will give me a higher expected return, or for a particular level of return, if I am not able to find a portfolio which will give me the least possible risk, which will give me a risk which is lower than Vx, then I say that particular portfolio is efficient, otherwise it becomes very inefficient. So I will collect a list of all the efficient portfolios, and inefficient portfolios directly can be ignored. Any portfolio which is inefficient, I'll directly ignore it. Out of this various efficient portfolios, which are for this particular level of risk, this is giving the highest possible return. For this particular level of return, this is having the least possible risk. So like that, over a combination of risk and return, we see for different combinations of risk and return, we could see these are the efficient portfolios. Now, once the identification of these efficient portfolios is done, the investor will try to rank them based on his risk taking. Based on his profile, risk taking means he'll choose how much standard deviation or variance is suitable to him, suitable to his needs. So the ranking is done purely based on the utility function, which particular combination of the risk and the return will enhance the satisfaction levels of the investor. So that is how an efficient portfolio is typically chosen, right? So now we know the computation of the mean and the variance. So let's try to take up one simple numerical. Try to see how we, once I know that the return of portfolio, return of the security X is something, return on security Y is something. How do I typically get into the portfolio construction process? How does covariance and correlation play a role in the portfolio construction? All these things we'll try to look at taking a very simple example, right? So let's look at a situation where we are talking about two securities A and B, and where A is having an expected return of 10%, B is having an expected return of 15%. Similarly, I'll look at the standard deviation of the returns. Let's say A is having a standard deviation of 12%, whereas B is having around 15%. So from here I can very well find out the variance, which is nothing but the square of the standard deviation. So here I'll say that A is having this as the variance, B is having this as the variance. And just for understanding, I will also build up the correlation that is existing between the returns of these two securities. For time being, let me say that the correlation is 0.5. And now we know the relationship. We know the relationship that correlation between A and B is same as covariance between A and B divided by the standard deviation of A times the standard deviation of B. So from here I can very well arrive at the covariance between A and B as the correlation between A and B multiplied by the standard deviation of A times the standard deviation of B. So the same logic I'll use here to compute the covariance between the two securities A and B. So I'll take it as correlation multiplied by the standard deviation of A multiplied by the standard deviation of B. So this works out to be the covariance. Now what I'll try to do is I'll try different combinations of A and B. So I'll say I'll take two different variables. So here I'll say I invest 0% in A, which means 1 minus 0, 100% is invested in B. Similarly, if I invest 5% in A, it means that I am investing 95% in B. Like this, let's say I will try to do an increment of 5% in A, and I will see how much. So in B it is exactly 1 minus of that. Now we have already seen the formulas that the expected return of the portfolio is WARA plus WBRB, which is the weighted average of the individual returns. So I'll call the return on the portfolio, I'll call it, I'll go with the same thing, W1 or WA times RA, the expected return on A, plus WB times RB, the expected return on B. So giving me that the expected return of the portfolio in each of the cases is going to be something like this. And what we see is the expected return on the portfolio is more or less a linear relationship. On the other side, I will also take the variance of the portfolio. We have seen that the variance of the portfolio is WA squared, the variance of A, plus WB squared, the variance of B, plus 2WA WB, the covariance between A and B. Same logic I am going to apply here. WA squared, variance of A, plus WB squared, variance of B, plus 2 W1 or WA times WB times covariance between A and B. So this has given me the variance of the portfolio going with this formula. So this happens to be the variance of the portfolio in all these combinations. So this combination means if I invest 35% of my money in A and 65% of my money in B, the expected return on the portfolio is going to be 13.25% and the variance of it is going to be 0.015. So from here, I'll even compute the standard deviation of the portfolio, which is nothing but the square root of the variance, which I get in this case. In each of these cases, I'm able to get the variance of the portfolio. Let me try to convert it into a percentage form. Now you could see it started 15, 14, 13, 12, 12, 11, 11, 11.5, 11.4, 11.3. And after that, again, it started going up 11.35, 11.4, 11.49, 11.79. And it has gone to 12. So which means somewhere in the middle, it has come down to the lowest point. And again, it started going up. Whereas if I look at the return, it is purely in a decreasing form only. Whereas the standard deviation has gone down up to a certain extent, and after that again it has picked up. So this is one thing. Now, which means there is some particular combination which will give me the minimum most variance. In this case, probably 70-30 is that particular combination which will give me the minimum most variance. How do I find that out? Okay, so my intention is to minimize the variance of the portfolio. We know that the variance is WA squared variance of A plus WB. What I'll do is WA squared variance of A. Instead of WB, I'll write it as 1 minus WA. 1 minus WA squared variance of B plus 2 times WA into WB. WB I write it as 1 minus WA, covariance between A and B. So I have to minimize this particular function. So if I have to minimize it, I'll take the first derivative of it with respect to the weightage. I'll take the first derivative of it with respect to the weightage and I'll make it equal to 0. So which makes 2WA VA, variance of A, plus variance of B times 2 into 1 minus WA times times minus 1 plus 2 covariance of AB, I'll take it as constant. Here comes WA times minus 1 plus 1 minus WA. So this is the derivative with respect to WA, and this I have to equate it to 0. So it's directly coming out 2 times variance of A times WA plus 2 times variance of B times minus 1, means minus 2 times variance of B, and plus 2 times variance of B times WA plus again the same minus WA plus 1 minus 2 WA here, and this is plus 1, so it becomes plus 2 covariance between AB minus 4 covariance between AB times WA. So this is equal to 0. So I collect all the WA terms on one side, right? Collect all the WA terms on one side, and probably 2 WA, 2 is across the same, so let me collect 2 WA terms on one side. It is becoming variance of A. I'll take from here, I take variance of B, and from here I take 2 covariance between AB, and these terms I take it to the other side. Again 2 times variance of B minus covariance between AB. Taking the 2 out on both sides, directly saying the weightage of A is variance of B minus the covariance between AB divided by the variance of A plus variance of B minus the twice the covariance between A and B. So this is the proportion of investment in A that will minimize the overall risk of the portfolio. So let's try to compute from here the risk minimized value. So if I really risk minimized, WA is what I will try to find out. The one that can typically minimize the risk, the WA. So for that we are using the variance of variance of B minus the covariance between A and B divided by the variance of B, variance of A plus variance of B minus twice the covariance between A and B. So this is telling me that if I invest approximately 71.43% in A, right, and the remaining is 1 minus of this, which is somewhere around 28.57% in B, that is going to be the optimal portfolio, which is going to mitigate my risk. The risk mitigation kind of a portfolio is going to come up in that situation. So probably it's as good as saying in one of them, just to see whether it gives me something more than this or less than this. What I want to try out is in one value I would like to replace it with 71.43. So suddenly it is giving me 11.34 itself. Even this is 11.34, but if I expand the decimal, it is 3389, whereas this is 3406. So this is the least possible standard deviation that is coming out, 3389. That is the least possible standard deviation that is coming out versus the 11.74 combination, which means this combination gives me the least possible risk for a given level of return. From the different possibilities of investment, if I am more interested in mitigating the risk to the fullest possible, I can see that this is the combination. Now, here comes the most interesting aspect, which is a typical graph. I'll try to go with a typical graph between, I'll take the standard deviations on the x-axis and the expected returns on the y-axis. Let's see what happens. I'll insert a simple scatter plot. Okay, I'm inserting a simple scatter plot by typically taking, so I look at risk, I call this as risk return graph. I'll take the standard deviations on the x-axis and I take the expected returns on the y-axis. Now you see what has occurred. This is a curve that is coming out, which is an indication or which is a pointer of the risk return relationship that is existing between the securities A and B. Right? It's a risk return relationship existing between A and B, which we are seeing that if I am taking the standard deviation on the x-axis, expected returns on the y-axis, the typical graph that is coming is more like a parabola, right? A kind of a hyperbolic or a parabolic. This is more like a hyperbola as such. In some cases it is purely, it will come out like a hyperbola. In some cases it may result in a parabola as well. Now here what I would try to do is, now let's keep an eye. Here the minimum most is somewhere around 11.34 and that is occurring at somewhere around 70. Now, just for the sake of understanding, I want to make this correlation close to 0. When the correlation is 0, I see even more a perfect curve that is emerging. And if I see the minimum variance is occurring when I invest 60% in A or 61% in A and 39% in B, wherein I am seeing that I am able to bring down the standard deviation close to 9.37, whereas in the earlier case it was around 11.34. Now make the correlation even minus 0.5. I see even more I am seeing that the movement is towards the lower standard deviation. And this is where it is saying it's better that you invest 57.3% in A, 42 in B, which could result in somewhere around 6.68%, the lowest kind of risk in terms of 6.68. And probably if I am taking the correlation as -1, it is clearly giving some kind of an indication that I can make it a zero risk portfolio as well. Because if you try to look at the formula WA squared variance of A, WB squared variance of B to correlation between AB, WA, WB, standard deviation of A, standard deviation of B. Now if the correlation is +1, if the correlation is +1, you could observe that this expression comes out to WA squared VA, WB squared VB plus 2WA WB sigma A sigma B. Now it is looking like A plus B whole squared expansion, because VA is nothing but sigma A squared, VB is nothing but sigma B squared. So I could very well write it as WA sigma A plus WB sigma B whole square. The same logic goes if the correlation between them is -1. If the correlation between them is -1, it becomes WA sigma A minus WB sigma B whole square. This is the variance. Now this I can make it 0. This obviously may not be 0, but this can be made 0, which is giving me that WA sigma A is given same as WB sigma B. So in our case, probably if sigma A and sigma B are 12 and 15, so it's as good as saying WA times 12% is WB times 15%. And it's also saying that WA by WB should be 5 by 4. So if I have invested in such a way that WA is 5 by 9 and WB is 4 by 9, which is around 44.4% in B, 55.5% in A, I could have made a portfolio variance of 0 in case the correlation between them is perfectly -1. So all we are trying to know, see from this kind of mechanism is correlation is playing a very important role in trying to decide the optimal portfolio combination. Correlation is a very important stuff, and it's better that I do a plotting between the standard deviation of the returns on the x-axis and the expected return on the y-axis. And this is also giving us another important thing, especially when the correlation is close to -1. There is some kind of a combination that will give me a risk-free kind of a portfolio, which will make my portfolio completely having zero risk. Right? So this entire story comes up, especially when we are working with two securities. But if I am working with n securities also, process is the same. My intention, right, even if I am choosing n securities and I am putting a kind of weightage of xi in each of them, my intention is always to minimize the variance of the portfolio. And here comes the variance means W1 squared sigma 1 squared, W2 squared sigma 2 squared, W3 squared sigma 3 squared, whatever are n, Wn squared sigma n squared, plus 2 W1 W2 covariance between security 1 and 2, 2 W1 W3 covariance between 1 and 3. Like this, it goes for all combinations. 2W1 Wn covariance between 1 and n, 2W2 W3 covariance between 2 and 3, which means it goes for NC2 such kind of combinations of covariances. So this is where I earlier said, if I require the variance of the portfolio, I require n different means, n different variances of each of the security, and typically NC2 correlations, and these correlations will go into covariances. So overall I require n into n plus 3 by 2 number of calculations to compute the mean and the variance. But yes, now using all those, so that is what comes out to be my variance. My intention is to minimize this variance, and I have a few constraints: x1 plus x2 plus so on xn, which is nothing but sigma xi. That should be equal to 1, which means I have to invest to that extent. And if at all I have some kind of an expected return, means x1 r1 plus x2 r2, whatever is the return that I am looking at, it should be equal to the expected return rx. So this is the typical equation or the structure that we have to plan out, especially when we are solving multiple securities as a part of the portfolio. And these kind of solutions typically are handled through the Lagrangian multipliers. Right, the Lagrangian multiplier is something which can establish a similar kind of outlook for us in terms of workout. Simply put, let's try to see if I am having 3 securities. Just trying to see how the Lagrangian is going to help me out. If I am having 3 securities, right, we are first looking at the variance. Variance is W1 squared sigma 1 squared, W2 squared sigma 2 squared, W3 squared sigma 3 squared, plus 2W1 W2, the covariance between 1 2, 2W2 W3, covariance between 2 3, and 2W1 W3, covariance between 1 3. This is the variance. Now the Lagrangian simply says whatever is the variance, whichever the one that you want to minimize, minus whichever are the constraints that you have. The one constraint that I have is the expected return, which is W1 R1 plus W2 R2 plus W3 R3 should be equal to some R, which is our expected return. This is one constraint. The other constraint is all of them should sum up to 1. Now what we typically do when we are expressing a Lagrangian is we first take a Lagrangian function, let's say some k. Lagrangian function k, all we say is whichever the value that you have to minimize minus some lambda times whatever is your constraint number 1, W1 R1 plus W2 R2 plus W3 R3 minus R. That is your first constraint. Then probably I'll call it as minus lambda 1 times this. I also have a lambda 2 times the next constraint, W1 plus W2 plus W3 minus 1. So I really need to minimize this particular function. And if I have to minimize this, okay, here we are talking of lambda 1 and lambda 2, which are typically called as Lagrangian multipliers. And typically this R1, they are typically the constraints, the constants which are constraining our relationship. So my intention is to minimize this variance. So any maximum minimum problem will take this particular function to be differentiated partially with respect to the various variables. So we'll do the differentiation with respect to W1 equate it to 0. We do it with respect to W2, we equate it to 0. We take it with respect to W3, we equate it to 0. We do it with respect to lambda 1, equate it to 0. We take it with respect to lambda 2, equate it to 0. So we'll get 5 equations. So if I just see for W1, first I'll differentiate this with respect to W1, comes out to 2W1 sigma 1 squared. With respect to W1, this is a constant, this is a constant, this is a constant, so I can ignore. So here this comes out to 2W2 covariance between 1, 2. And with respect to this, it comes out to 2W3 covariance between 1, 3. So this part is 0. So I'll get my first, and again there is a few more W1s are there. So here it is coming out to minus lambda 1 R1. This also contains a W1. And here also there is a W1 which is minus lambda 2. So this entire thing is becoming 0. So probably I will get one expression. So if I simplify this, I'll get an expression 2W1 sigma 1 squared plus 2W2 covariance between 1, 2, 2W3 covariance between 1, 3 minus lambda 1 R1 minus lambda 2 equal to 0. Same logic, if I take it a little bit more deeper, it becomes 2W1 covariance 1, 2, 2W2 squared sigma 2 squared plus 2W3 covariance 2, 3 minus lambda 2 R2 minus lambda 2 is equal to 0. And the third one comes 2W1 covariance 1, 3, 2W2 covariance 2, 3, 2W3 sigma 3 squared, 2W3 sigma 3 squared minus lambda 3 R3 minus, sorry, this is lambda 1 only, minus lambda 1 R3 minus lambda 2 is equal to 0. And now when I have to differentiate that particular with respect to lambda, it is coming out to W1 R1 plus W2 R2 plus W3 R3 is equal to R. And finally, if I am doing it with lambda 2, it is coming out like W1 plus W2 plus W3 is equal to 1. Now if you see these 5 expressions, if I solve, I'll get W1, W2, W3. And if you look at it, the best way for me to solve is write this in the form of a matrix. Right? If I write it in the form of a matrix, wherein I'll take variables W1, W2, W3, lambda 1, lambda 2. So I'll write it in such a way that AX equal to B. So a simple way for me to look at here is I'll take 2 sigma 1 squared, right, 2 covariance 1, 2, 2 covariance 1, 3 minus R1 minus 1. Similarly, 2 covariance 1, 2, 2 variance or sigma 2 squared, 2 covariance 2, 3 minus R2 minus 1. This becomes 2 covariance 1, 3, 2 covariance 2, 3, 2 sigma 3 squared minus R3 minus 1. And here it becomes R1, R2, R3, 0, 0. And the final one will become 1, 1, 1, 0, 0. This is my matrix A. This I multiply it with another matrix W1, W2, W3, lambda 1, lambda 2. This is my matrix X, and this is where I equate it to B, which is 0, 0, 0, R and 1. Now this is a simplification, and probably this is looking like AX equal to B. For computing X, all I require is A inverse B. Take the inverse of this particular matrix, multiply it with B, I get W1, W2, W3 as the solutions of that particular expression. So this is what is the typical Lagrangian multiplier model. Once I am getting my matrices, and another way to look at here is you look at the first part, this part. It is purely coming out as twice the covariance. Now if you look at it, this part is nothing but twice the variance covariance, right? Wherever the variance is there, the covariances are there, take the twice of all of them. So this is becoming the twice the covariance, and here it is becoming minus the expected values, and here it is minus ones. And so wherever are the expected values, they are coming out, and this is the minus ones that are working out. Similarly, here I take the expected values transpose, because I am getting R1, R2, R3 in this way. Here I had R1, R2, R3 in this way. And similarly here 1, 1, 1 I had minus here in this way. Here I have the transpose. So I'll say 1's transpose, and rest all these numbers are typically going 0. This is a typical way I can quickly plan out even if there are multiple variables. So if at all I have to talk about a quick matrix way, if I have 4 variables, what is the quick matrix way? I take it as 2 sigma 1 squared, 2 covariance between 1 2, 2 covariance 1 3, 2 covariance 1 4. First let me write this out. 2 covariance 1 2, 2 sigma 2 squared, 2 covariance 2 3, 2 covariance 2 4, 2 covariance 1 3, 2 covariance 2 3, twice sigma 3 squared, 2 covariance 3 4, twice the covariance 1 4, twice the covariance 2 4, twice the covariance 3 4, twice the variance sigma 4 squared. Now all I do is minus R1 minus R2 minus R3 minus R4. Here also I take it R1, R2, R3, R4. Similarly, I'll take minus 1, minus 1, minus 1, minus 1. Here I take 1, 1, 1, 1. Put zeros here. This is what will become my matrix A, and this would be multiplied with another matrix W1, W2, W3, W4, lambda 1, lambda 2, which would be equated to B. So this is the quick way out in terms of determining the weightages W1, W2, W3, W4 to finally arrive at the appropriate combination which is going to mitigate the overall risk of the portfolio. And what we typically see here is all these things, one in a matrix form, one in this kind of a form, can be solved through a pen and paper kind of a mode, but the same logic can be solved if I am using a tool like Excel. We can very well use a built-in function called solver, which will try to come out with the best possible solution of W1, W2, W3, W4, which is the most optimal solution, which will reduce the variance of the overall. And finally, I can very well, once I have got all my W1, W2, W3s, I can very well substitute them in the equation for the variance. Or probably once I have got my W1, W2, W3, it's as good as take W1, W2, W3 in this form. Take the variance covariance matrix between the two, which is nothing but variance, covariance of 1, covariance 1, 2, covariance 1, 3. Covariance 1, 2, variance 2, covariance 2, 3. Covariance 1, 3, covariance 2, 3, variance of 3. So this is the variance covariance matrix, and multiply with the weights again like this. This is what is the variance of the portfolio that we are trying to get. And all we have to understand is the variance is quadratic, right? The variance function is more quadratic in nature, whereas the expected return is more and more linear in nature, right? So the expected is always linear, whereas the variance is quadratic with respect to the mean. And we are typically at any point we are trying to plot the expected returns and the standard deviations on a graph with standard deviation on the x-axis and the expected return on the y-axis. And this is where this kind of a graph, whatever may be the correlation. So for me, let me again go back with a correlation, let's say of 0. Now this particular graph, which is talking about a curve like this is a typical risk return kind of a curve. And this particular point where the standard deviation appears to be lowest. Here we are seeing up to a certain point. From this point, there is a standard deviation. As the standard deviation is increasing, the return is also increasing. Whereas below this, as the standard deviation is increasing, the expected return is falling. And this particular point is called as the global minimum. Means for this particular combination with these two securities, or with this whatever securities we are using, for this combination, the minimum most variance is going to occur for that particular combination. That is called as the global minimum for that combination of standard deviation and the return. And the curve which is typically above it. This is the part of the curve which is above this global minimum. So typically we see that the curve is like this. This is the global minimum point. So that portion of the curve which is above the global minimum, we call it as efficient frontier. Why? Because this is that particular combination for different levels of risk. I am getting the highest possible return, and for a given level of return I am getting the lowest possible risk. So all these portfolios typically are a set of efficient portfolios, and the curve from here to above is called as efficient frontier curve, making all the portfolios on this curve being efficient, whereas all the portfolios which are below, they are inefficient. Why they are inefficient? Look at this. For this level of standard deviation, efficiency means I have to get the highest possible return. But this is giving me this much of a return, whereas there is something which is giving me much more higher return. So I prefer this combination rather than this. So this portfolio will become completely useless. So that is where we say below that global minimum of that curve, all the portfolios are inefficient, and above it they are more and more efficient. So that is one more important concept that comes out. Now that I know that these are all my efficient portfolios, these are all the efficient portfolios that are available in the market, which are providing the highest possible returns for the given level of risk and the lowest possible risk for the given level of return. So now that I know that this is the efficient frontier, how do I choose for me? Now is what coming out for me, for an individual investor, which is the efficient, because all these are efficient portfolios only. But for me, looking at my risk profile, the individual specific, investor specific, which is the typical combination which is ideal. Is this combination ideal? Is this portfolio ideal? Is this ideal? Is this ideal? Which one is ideal? This is where we try to club it with the indifference curves. This entire curve, we try to, this efficient frontier, we try to club it with the indifference curves. We know that the indifference curves are typically those particular curves where the investor derives similar level of utility along the curve. So let's say if there are these kind of indifference curves, okay, this particular curve, this combination, the investor is purely indifferent. Similarly, this or this is purely indifferent. This or this is purely indifferent. But between this and this is more and more, this is giving him more and more utility. This is giving him even more utility. So looking at from a satisfaction perspective, the one above it are more satisfactory, the ones below it are less satisfactory. But along each of those curves, the satisfaction, the utility which the investor is going to derive is going to be the same. Now what we are typically doing is, on this we try to superimpose the indifference curves. We try to superimpose the indifference curves on this efficient frontier, where I see that the indifference curve or the efficient frontier to which indifference curve it is acting like a tangent. To which indifference curve the efficient frontier is a typical tangent to an indifference curve. That particular point is the combination of the desired risk and the expected return for this particular investor to typically choose. And that is what is called as the most efficient portfolio for this particular investor given his risk and return profile. So wherever I am seeing that the utility function is more quadratic in nature, quadratic is it is behaving in kind of a parabola like this. So we can very well expect where we typically see that the efficient frontier is typically acting as a tangent to it. Based on the mean and the variance of the distribution, we should be able to find out the efficient set of portfolio or efficient portfolio for this particular investor. And here, if I am looking at only the mean and the variance, to a large extent, it gives me a kind of opinion that the returns need to be more normal, because the distribution of the returns, if it is more normal, it is characterized by the mean and the variance. But in some cases, if there is, let's say, skewness, I may want to construct a three-dimensional kind of a space, because skewness is a measure of the third moment. So I can very well construct it in 3 dimensions, try to do the same kind of analysis in 3 dimensions. But what we typically are seeing in the real world is, though conceptually all these are possible, we are still seeing that the portfolio selection is purely happening based on the mean and the variance, even though the returns are not normal. Even though they are not normal, the skewness and the higher dimensions are typically not taken into consideration. So from a practical perspective, the usage of all the higher models is typically not existing. People are still going with the mean and the variance kind of a framework itself. So this is how we can try to construct the efficient portfolios, effective portfolios for the investor, looking at purely the mean and the variance using this concept of modern portfolio theory or mean variance portfolio theory. All right.